The right triangle similarity theorem says as follows. Given a right triangle, let's start with any old right triangle. If I'm use and. It's a pronoun choice. If an altitude is drawn from the right angle to the hypotenuse, then the following is true. Then the two triangles created are similar to each other and similar to the original triangle. We're going to first start by identifying some triangles in kind of this visual fashion by re-sketching these triangles so all the corresponding angles are the same orientation and the same spot on the paper. So to start here, I'm going to redraw this big right triangle and just a very rough sketch. Here's my right angle, and it's labeled triangle A, B, C. This is my big right triangle. I'm going to next look at, again in very rough fashion, I'm going to look at one of the smaller right triangles. And I like going from largest to smallest. So we're going to look at kind of this medium size right triangle. And I want to visualize re-sketching this so that all the corresponding angles are in the same orientation as the largest one. So for example, on the top here, I want to make sure that my right angle gets up here. And what's the right angle in my medium-sized triangle here? What's the right angle in my medium-sized right triangle? D. So I'm going to move this around so that D is now on top. What angle in my medium-sized triangle here corresponds to angle A in my large right triangle? What angle in my medium-sized right triangle corresponds to angle A in the large right triangle? Joel? It's still A. Yeah, they're shared, right? It's still A. This is still angle A. So then by the third angle theorem, what angle has to correspond to angle C in my medium-sized right triangle? What's the only one left over? The only one that left over has got to be angle B. So all I've done is I've taken this medium-sized right triangle and I've just rearranged it so that it's in kind of the same, all the angles are in the same spot as my original triangle. So I'm going to do the same thing with this smallest triangle that I just made. The same game. I still want the right angle here. I want whatever angle has got one angle's down here. So in my smallest triangle, what's the right angle? D. In my smallest triangle, what angle should go down here? What angle corresponds to angle C in the big triangle? C, they're both shared. So then what's left over? That forces this smaller part of B to correspond to have the same measure as angle A. By doing what we've done here is by rewriting these with these smaller triangles in the same orientation as the larger one, we've really made writing our similarity statements and identifying what the similar triangles are, we've made the life pretty easy. Because essentially, so now we have the similar triangles all in the same spots. So if we need to write a similarity statement, recall that we're going to label the triangles so the corresponding vertices are in the same spots. So when I want to write a similarity statement, say triangle, how about ABC? Triangle ABC is similar to which two triangles? ADB. And it's also similar to which triangle? If I go ABC, then I went ADB, I better go BDC. I'm going to write similarity statements based on this. So I've taken these triangles. If you think like a visual thinker, you've like basically cut these triangles out. You flip the two smaller ones and then rotated them so that the corresponding angles are all in the same spots. Okay. What I'd like you to do right now is on your own or with someone sitting next to you. Let's try to do that same thing with the second example. And if you finish that before we go over it, you can use that same line of thinking to attempt to find, to set up some proportions in the bottom two on your notes. And as a word of warning, it may be a good idea to go through and actually label the triangles below. It might help you when you're trying to redraw them in the bottom examples. So let's see. I would do this. I have RST let's see. W is the right angle. T is the double hash, and S is down here. W, R, S. So hopefully our similarity statements are something as follows. Either RST is similar to SWT, similar to RWS. Other arrangements could be like SRT, similar to WST, similar to WRS. How about like TSR is similar to TWS, similar to SWR, and any other combination, as long as those parts correspond. Okay. We're going to take this line of thinking and apply it to now try to find some missing pieces. For triangles that don't have the vertices labeled, let's go ahead and label them. I'm going to label the first one very blindly in A, B, C, and D. Okay. Notice the vertices are not labeled for this second one, for this first example when we're trying to find some lengths. I'm going to go ahead and label them myself because when I'm doing this visual method, it's going to really, really help me as far as getting the pieces in the right spot. So I'm going to attack this in the same way I just did. I'm going to redraw my three triangles. I have A, B, C. And I'm going to fill in the things that I know. I'll go back and do that after. I want to get the triangles drawn. My middle-sized triangle, the right angle is D. B corresponds to B in both cases. And therefore, this third segment, if I label these. My single hash in this triangle has to be C. And similarly, my right angle in my smallest triangle is still D. The A corresponds to A. And this is forced down to B, C. I'm going to fill in the segments that I know. So from the original. So for example, I know that segment AD is 2. So anywhere down here I see an AD, I'm going to label it as 2. So AD is 2 right here. I know that segment CD is length Y. So anywhere I see a CD is a Y. There's a Y. There's a y. I know that segment BD is 8, so I'll fill in 8 anywhere I see a BD, which I believe is right here. And the last segment I know, I can figure out that AB has length 10. So fill in a 10 up there just for giggles. Okay. With this setup, what's a proportion I could write to solve for y? Kelsey? Could say 2 to y is y to 8. Is one proportion you could write, absolutely. You could have also done like y to 2 is 8 to y to 2 is 8 to y. That's really the gist of it. You could solve that proportion, cross multiply, square root, and you end up with what y is 4. Boy, oh boy, what does this equation look a lot like? Holy cow. That equation looks almost identical. In fact, it is identical to a geometric mean setup. Y, in this case, is the geometric mean between 2 and 8. Or, if we go back to our original triangle, y is the geometric mean between 2 and 8. The altitude was the geometric mean between the two parts of this hypotenuse that we created. The altitude, by virtue of our proportion we set up in drawing these triangles, is the geometric mean between these two segments. This is actually going to drive the first formula that we have on the back side. Solve, and we believe you get y is 4 in this case, right? Let's do the same thing for the second triangle. I'm going to have to erase some of this so I can get to it. Notice that in this triangle, I'm not told what the altitude is. So we're probably not going to be able to just use that kind of same pattern that we just saw. But with any luck, we'll arrive at the second one. Let's label this triangle before we go any further. Let's do the same kind of game here with redrawing. But in order to do the redrawing efficiently, let's label this triangle. So rather than being bland this time, give me some examples here. I'm not very creative here. Give me one. Paige, give me one. P. Paige, you're about as creative as I am. Okay, Paige has already chosen P. Anyone want to volunteer another letter? Joel?
Smiley face.
Smiley face. If you're lucky, I'll accept that. Okay, P, smiley face. What's another variable we could use? Come on, we need 2 more. This shouldn't take us all day. Someone volunteer something. Alex, you got something to tip your tongue. We're not using numbers. Can't use numbers.
Wow.
Need to tell you numbers. Isabel. I. One more.
G.
Ben. Money sign. Okay, sure. This will be non-traditional, but we'll make it happen. Okay, let's redraw these Let's redraw our right triangles with the corresponding parts in the same spot. Right triangle, P, smiley, and I. Let's see, middle-sized triangle is, dollar sign. Let's see, I corresponds to I, and smiley is now the smaller angle. And let's see, our smallest triangle here, right angle is, dollar sign. Right angle is dollar sign. Let's see, P corresponds to P. And that leaves, what, dollar, let's see, smiley face over here? Great, non-traditional here. Doesn't really matter what those labels are, because now we'll fill in the numbers we know. So P to dollar sign is 1. P to dollar sign is 1. Let's see. Smiley face to I is X. So smiley face to I is X. Smiley face to I is X. Let's see. Dollar sign to I is 4. Dollar sign to I is 4. else do we have here? P to I. Oh, P to I is what's its length? 5. Okay. So looking at this, what's a proportion we can set up to try to find what x is? Kelsey? So you say 5 to x. 5 to x is x to 4. Or 4 to x is x to 5. Would be another proportion. Notice again, we're in kind of the same spot. That x, this missing thing that we didn't know, ends up being the geometric mean of these two numbers. Well, let's go back, let's dig back a little bit, try to figure out where these numbers came from. Where did 4 come from? 4 was right here. 4 is a part of the hypotenuse. Where did x come from? Smiley face to I. That's what would we call this? What would we call the segment that x is in the big triangle? What's a name for it? A leg. X is a leg of the original right triangle. 4, also notice, 4 is adjacent to this same leg. 4 is adjacent. It touches this leg. Where did the 5 come from? Okay, what would we call the segment that we got 5 from? The whole hypotenuse from the original right triangle. So what we could say is that a leg of the original right triangle is the geometric mean of two things. Of this segment that's adjacent, of this part of the hypotenuse that's adjacent to that leg, and the whole hypotenuse. It's going to be the driving force behind our second idea. Okay. By solving this, you get x is equal to the root of 20, which is 2 roots of 5. Let's formalize these two patterns that we kind of saw as theorems on the backside, so we don't have to redraw triangles every time. We'll make life less crowded. Okay. We'll start with the first idea. The geometric mean for altitudes theorem is what we'll call this. It'll be simply put. This is the altitude say the altitude as we've constructed it in the front side. The altitude is the geometric mean of the two parts of the hypotenuse. As a formula, this theorem boils down to part 1 over altitude equals altitude over part 2. As a formula, they could boil down to this. Note that we could solve this right triangle without all the redrawing by observing that x is the altitude, 3 and 12 are parts of the hypotenuse that the altitude is divided, and therefore x must be the geometric mean of these two, or 3 to x is x to 12. Part to altitude is to part. 3 to x is x to 12. Solving, we end up getting x is, we should end up by cross multiplying square root, we end up with x is 6. Via this formula. In our second example, Second example is very similar setup. I know I'm going to involve the altitude, and I can figure out what the two parts of this hypotenuse are that I've divided up. I didn't explicitly tell you as I did in the first one, but we can quickly figure them out. This part's 15, therefore what's this chunk? 5. So using this theorem, rather than redrawing all those right triangles, I could say that part is to altitude as altitude is to other part. Or x is root 75, which is 5 root 3. Without needing to redraw, if we go directly to the formulas, you can go this route. Okay. We'll also formally state the second pattern that we saw, the geometric mean theorem for legs. It said the following. It said a leg of a right triangle is the geometric mean of the hypotenuse and the adjacent part of the hypotenuse. Again, as constructed. Adjacent part, yes. Adjacent corner. The adjacent part, or the part that touches the leg we're dealing with. Of that, as constructed before. So as we drew the altitude from the right angle to the opposite side. As a formula, we say part to leg is leg to hypotenuse. Be as a formula this theorem boils down to. As an example, our first problem here, notice that I have a right triangle as we've constructed. I also have, I don't know really any information about the altitude, and from the way the diagram is constructed, it doesn't look like I should need to, because I don't have a variable or any numbers or anything written about it. So that kind of is driving us to try to look at the second piece. Do I know what one of the legs are of this right triangle? Or do I have at least a variable for it? Yeah, I do. What's the leg that I care about in this right triangle? 6, leg being one of the non-hypotenuse. So if I'm thinking my proportionality, the leg has got to be 6. Leg is the geometric mean. So the other things I need to know are the whole hypotenuse and the adjacent part to that leg. Well, do I know one of those? What are those two things? For example, what's the whole hypotenuse of this triangle? 12. What's the part? Now the part again is the adjacent part of the hypotenuse. Adjacent meaning touching this leg. So what part of the hypotenuse is touching this leg? This segment, which is length A. That's what we're trying to find. With this proportion, we can solve for A. Cross multiply and solve. In this case, you get 12A equals 36. A is 3. Note that in this example, A was not the geometric mean. The variable is not always the geometric mean. Scroll this up. The variable is not always the geometric mean. we're going to set our proportions up such that either if we're using for the leg theorem, we have part, leg, hypotenuse. Or if you're using the altitude theorem, you have the two different parts of the hypotenuse and then the altitude. Okay. Let's set this last one up and then get your homework out. Let's see, we're not using the altitude, so we must be using this leg idea. What are some things we can fill in? X, where does X go? What is X called in this case? It's a leg, so what is the leg in this? Where does our leg, the length of our leg go? The leg is the geometric mean, so it's going to get repeated. What will we call 9? It's the adjacent part. What's 11? It's just the other part that we don't really care about in and of itself. But we'll use 11 to get what? The whole hypotenuse, which is 20. Okay. This whole segment has got to be 9 plus 11, which is 20. Okay. We don't care about 11 in and of itself because we are looking at the leg here. Now, if I asked you, how about we'll extend this just a touch. What if I gave you a second variable here, y? What's a proportion you could use to set up to find y? What's a proportion you could set up to find what y is in this case? Well, what is y in this setup? What do we call the segment that y is? It's an altitude, and it's the geometric mean of what two numbers? 9 and 11. It's that first theorem. So if I asked you to find y, we could say 9 is to y as y is to 11. If I extended the problem. Cross multiply, solve, go from there.